I'm going to solve problem number 66. This is kind of a prototypical kind of problem involving forces. And the approach that you use to solve these problems is going to be the same approach for any kind of force problem. You're always going to do the same exact things. So in this problem, they ask what force must be applied to a 100 kilogram crate on a frictionless plane inclined at 30 degrees to cause an acceleration of 2 meters per second squared up the plane. Okay? A lot of words there. So let's draw the picture. We're going to have a box on an inclined plane. That plane is inclined by 30 degrees. Here's the box that I'm pushing up this inclined plane. The mass of the box is equal to 100 kilograms. The force that I'm applying is up the incline, so this is the direction for my force of my push. And we want an acceleration of this box as we're pushing it up the incline of 2.0 meters per second squared. So this is everything that the problem gave us. When you're working with force problems, what you need to do is identify all the forces that are acting on your object. In this one, I'm pushing something up an inclined plane. So I am applying a force that's going up the incline. If that was the only force that was acting, this thing would go flying up. What other forces are acting on this?
Friction.
So gravity, I heard gravity. Where does gravity go?
Down.
Down. Straight down. So what we're doing is we're going to draw a free body diagram. This is identifying all the forces that are acting on this object and the directions that those forces are going. So I have, imagine in the center of the box, I have gravity acting straight down. And let's call gravity Fg. I heard somebody say friction. Is friction acting on this?
No.
No? Why not? Because it said it's a frictionless plane. So no friction in this one. If there was friction, we need to talk about it. We are pushing it up the incline, so what direction would friction go? Friction? Go down. Friction always opposes the direction of your motion. What if I were pushing this down the incline? What direction would friction go? Up. Okay, friction always opposes your motion. Okay, what other forces are acting? Normal force, where does that go? The normal force is a force that exists when you're sitting on any surface, so it's always perpendicular to that surface. So if I wanted to identify the normal force of, let's see, what is this saying now? Mayday. I put it on the table. The normal force is perpendicular to the object itself, perpendicular to what you're sitting on. So I'm sitting on the table, the normal force would be acting straight up. If I put this onto an incline, I can't do an incline very easily. Let's do an incline. I put it on an incline. What direction is the normal force going? Is it going straight up? No, where is it going? It's going perpendicular. As I make this a steeper angle, the normal force changes. Force always perpendicular to your surface. Okay. So, gotta draw a normal force. But that only exists because you're sitting on top of a surface. If I had a bucket that I was hanging, so this bucket, if I'm just holding this, I'm exerting a force on the bucket. I have tension in this string. Is this sitting on any kind of surface? Is there a normal force here? No normal force. What forces are acting on this? Gravity? Where's gravity going? Down. What else is acting? Well, is any other force acting? Tension. Where does tension go? Tension in the string, but what direction does tension go? Up. How do you know it's not going down?
But then the object would be falling down.
The object would be going down, right? It's not moving, so if I have a down force, I need an up force. Okay, in this case, is this object moving?
It
It is.
It is. It's going up the incline, so I have some sum of forces. And that's what you want to do next with these kinds of force problems. You want to write Newton's laws and identify the sum of forces on everything. And the other trick that we want to do here is instead of using a coordinate system that's kind of x and y, so x going up or x going to the left and y going up, you want to rotate your coordinate system. So what we're going to do is we're going to take our coordinate system, normally up and over, and we're going to rotate it so that it's going along the incline. So instead of going left and right, we're going to create a coordinate system so that I'm going to say that anything that's going up this incline is going in the x direction. Anything that's perpendicular to the incline is going in the y direction. This simplifies the problem by rotating your coordinate axis. Instead of just going up and down and left and right, we rotate it. How much am I rotating it by?
45.
45, 30?
30?
30 degrees. Why 30 degrees?
Because that's the angle.
That's the angle that I have to rotate by to get along that incline. 30 degrees. So I rotated my coordinate grid 30 degrees. We also needed to draw on that normal force. Let's draw on that normal force perpendicular to the incline. Okay. So now I need to write down the sum of forces that are happening in each direction. Newton's second law gives us an equation for sum of forces. What does Newton's second law say the sum of forces is? Mass times the net acceleration. Whatever acceleration I have, times the mass is the force. So what I have to do now is I have to split this into the x and y directions. Whatever goes on in the x and whatever goes on in the y. So in the x direction. Let's identify some forces. X direction. What forces, I'm going to say, we have a choice. We can choose whatever we want. Do you want things going up the incline to be positive or things going down the incline to be positive?
Up.
Okay, so let's say any forces pushing you up are going to be positive. So what are all the forces that are pushing you up the incline?
F push.
F push. Anything else?
That's it.
Nothing else putting it up the incline? Okay. Is there anything pulling it down the incline?
Yes.
Gravity.
FGBX.
Gravity's pulling you down. But gravity, looks like gravity is at an angle relative to our new coordinate system, isn't it? So if I draw in that new coordinate system right here, that's my y, and then that's my x. Right? I spun my coordinate system. I have a new coordinate system. So I need to take this FG and I need to break it into a right triangle so that I write the components of each part of this force that are acting in the x and y directions. So what I need to do is use that kind of tip to tail method of drawing vectors. I need to extend this vector downwards and draw a right triangle. So that's the amount of FG that's acting in the y direction. So I draw that down and let's call that FGY. And I need to know the amount of FG that's acting in the x direction. So I draw in the x direction. So I use this to draw a right triangle to break the FG into the pieces of FG that are going in my new coordinate grid. Things that are perpendicular to the incline and things that are parallel to the incline. This can get a little bit tricky. You'll get used to it with practice. The last thing we need to do in this triangle, in order to calculate stuff in the triangle, I need to know an angle in there. I know, using geometry, that this angle up top is the same as the angle that you rotated things by. We can calculate that. We can go through and do a math proof to prove this, or you can just trust me. Anybody want me? How many just trust me? Anybody want me to prove it? Good choice. Okay, so we'll just trust that, and we can use that for any kind of problem like this that's on an incline. draw your incline, rotate your coordinate system, draw that little triangle, and then that angle that's up there at the top is always going to be the angle of the incline. Okay. So now I need to keep going with this F push equation. I have F push pushing me up. What things do I have pulling me down the incline? Along that x-axis, along the slope. I've got FGX. It's the only force that is acting parallel to the incline pulling me down. Okay? And that's got to be equal to the mass times the acceleration in the x direction. Okay? I'm asked to solve F push. So F push, let's get F push by itself. And that has to be equal to mass times the acceleration in the x direction plus Fg sub x, the x piece of gravity. I have to find F push equals m. Do I know what m is?
Yes.
How do I know m?
It was given.
They gave it to us. How about a? Do I know what a is?
Yes.
Yeah, the grades we all want to get. It's the acceleration that was given 2 meters per second squared. Fgx, do I know what that is? I can calculate that. I can find that in terms of Fg, the force of gravity. What is Fg? Force of gravity. What's the equation for Fg?
Would it be?
Gravitational acceleration.
Mass times gravitational acceleration. Fg equals mg. This is perhaps the most important equation for forces. I tell students this every year. I told Alyssa's class this. When I was learning this, I used to actually just chant this as I was going to sleep, so I would never forget it. Fg equals Fg, Fg equals Fg, Fg equals Fg, Fg equals Fg. Do not forget that. That'll pop up on an exam. I'll make it like a 10-point bonus on an exam. What is Fg?
MG.
It's mg. But in this case, what is g equal to? G is the gravitational acceleration. How big is g?
Would you always say like bigger
It's 9.8 meters per second squared, and I'm going to point something out because I heard a couple of people say negative. Right? In kinematic equations, we use it as negative. Here, use just the magnitude of g. Because I've taken care of the direction using that right there. That negative sign tells me the direction the gravity is acting. So I don't plug it in also with the g. So in force problems, g is positive. Kinematics problems, g is negative. Okay? Because I take care of the direction. This negative right here, that's the negative that would go into the g. Pulling it down. I take care of all the directions when I'm writing out my sum of forces by writing that equation. Okay, so just use the magnitude of g. That's what we have going on there for mg. Now I need to write fgx in terms of f push. In terms of fg. Because do I know what the mass is? I know what m is. Do I know what g is?
Yeah.
What is g? 9.8. Positive or negative?
Positive.
Positive, because we're working with forces. And then I need to figure out how much of fgx is mg. So I have a right triangle there. What side of the right triangle do I have? I have that angle 30 degrees. What is fgx relative to that 30 degrees? Adjacent or opposite? Opposite. So what trig function can I use to get that?
Sine.
I can use sine. So if I write down the sine of 30, that's equal to the opposite side
The hypotenuse.
over the hypotenuse. Opposite over hypotenuse. The opposite side there, if I look at the 30 degrees, there, opposite side is fgx, the side that's opposite. So that equals fgx. So sine of 30 equals fgx over hypotenuse. Well, how big is the hypotenuse? Fg?
FG.
Fg is the hypotenuse. So I'm trying to find fgx so that I can plug it in for fgx down here. I can multiply both sides by fg. Multiply by fg. Multiply by fg. Fg cancels on the right-hand side. I see that fgx is equal to fg
times sine of 30. I have horrible handwriting. So what was FG again? I forgot.
MG.
FG is MG. Times sine of 30. And that equals FGX. So now I can plug that in over here. And F push is going to be equal to mass times acceleration in x direction plus m times g times sine of 30.
Good gosh.
So F push is the mass. What was the mass? 100 kilograms. What's the acceleration?
2 meters per second.
2 meters per second squared. Plus the mass. What's the mass again?
100.
100 kilograms. What's G?
9.8.
9.8. Positive or negative?
Positive.
Positive. I'm just going to scream in anguish when I get somebody's exam and they put a negative 9.8. It's just, oh. Times sine of 30. What mode do you want your calculator to be in? Degrees, because that is 30 degrees. So take this and plug it into your calculators. If it hasn't become apparent by now, you should always bring a calculator to this class. You should all have a calculator, and you should always bring it. Every single class. Every single class you need a calculator. Not this calculator, this one sucks. Why? Because you can't use this on your exam. Because you could Google the answers. And it's just a pain in the butt to type in things on the cell phone calculator. So take out your calculator, plug this in, and calculate this. And find that F push is equal to 690 newtons. Any questions on this problem? This is a prototypical force balancing problem for something sliding up or down an incline. I could change lots of things about it. I could have the box sliding down the incline. I could have the box having no acceleration. Tons of things I could do.
Friction.
I can add friction. We'll do that in chapter 6.
Springs.
I could put in springs. I could put in pulleys. I could change the incline. I can tell you gravity acts in reverse. What happened if what would you do with that? If I told you gravity now acts up, what would that change here?
I would try to fly.
Plus sign of push plus.
You would change the sign of this to plus.
You also try to fly.
Your box would be flying away then. It would be very weird. But I could do it. All right, let's do the y direction for this as well. So let's write down the sum of forces happening in the y direction. So remember, y direction is not up and down. Y direction is perpendicular to the incline. What forces do I have to acting up, perpendicular to the incline? Normal force. So I've got the F in force. And then what forces do I have? Well, any other forces acting up the incline? F push is pushing me up the incline, but it's not perpendicular, right? So I need only perpendicular. What's that? FGY. And what direction is that going? Is that going up or is it going down?
Down.
It's going down. So what do I do with that?
Minus.
Minus FGY equals 0.
Yeah.
How did I get 0?
Because
Because there's no motion
The box is accelerating. It's accelerating at 2 meters per second squared.
along the incline.
That 2 meters per second squared is along the incline. So along the incline is this. If I were accelerating in the y direction, I'd be bouncing up and down. I'm not bouncing along this incline, I'm sliding along it. So all the acceleration is in the x, so the acceleration in the y because it's not bouncing up and down, mayday. Acceleration on the y is 0. So that sum of force in the y direction has to be equal to 0. Okay? FGY. I can find what FGY is. Let's look at this. What side of the triangle is FGY?
Adjacent.
The adjacent side. So cosine of 30 is equal to FGY over FG. So FGY equals FG times cosine 30. All right. So that gets me the y direction, and I can plug that in. FGY is equal to mg times cosine 30. Fn minus mg cosine 30 equals 0. So I can now find that the normal force is equal to mg cos 30. So that's 100 times 9.8 times cosine of 30. Somebody plug that into your calculator. Tell me what you got. We have 848 newtons. Going once, that's one answer.
Well, 849. Should we round it?
849 newtons.
Why did you say Fn minus Fy is 0?
Fn minus FGY is equal to 0, because if I look at this, and I want to know how fast this is going. I have an acceleration that's 2 meters per second squared. That acceleration is along the incline. In the y direction, the normal force is perpendicular to the incline. So because this thing isn't going, bouncing along the incline, its acceleration in the y is 0. Does that even make sense? I've been doing this for years, bouncing along the incline, and I'm actually not confident that that makes any sense to me. Any other questions? Más preguntas.
For the net force, you would add the two numbers you got, the x and y direction. Yeah, x and y direction.
If I ask for what's the total force acting on this, then yeah, you could do the adding in quadrature.
Net and total is the same.
The net or total force would be F push squared plus Fn squared square root. Okay. I can. So you got 848 or 849, depending on how you round and how your calculator rounds. Those are the same number for me. I'm not that big. If I calculated 848 and somebody else calculated 846, because your calculator rounded differently, fine, we go. Okay. Any questions on this one? So your practice problem is basically to do another one that's almost exactly like this and try to go through this process and figure it out yourself.
I got my table.
I'll come talk to you. Any other questions before I release you to work? Okay, me and Alyssa will circulate. Ask us any questions you have.
Right. Clean sheet of paper.